Oh yeah, I remember the EcoCar team has gone somewhere. Yeah, and that's why this part of the class is missing. Okay. I have to leave early today, so I'll finish the lecture by 1:30. We were talking about proof of Lagrange multiplier theorem. And I want to remind you of the setting. So I define fk of x as f of x plus k over 2 norm of hx square plus alpha over 2 x minus x star square. And I define my set S as x such that x minus x star less than equal to epsilon. And I define xk as argmin fk of x. X is in set S. And there are a few results that I want to prove. So the first result that I want to talk about is that xk converges to x star as k goes to infinity. And the second part that I want to talk about is gradient of fkx xk. This is equal to 0. And then we will take the limit k goes to infinity, and I'm going to get lambda star. So I'm going to analyze this particular equation, and I'm going to get the expression for lambda star. And that would prove the first order necessary condition for optimality. The second order kind of goes the same way. You look at the second derivative and then make appropriate adjustments, and you get the second order necessary condition, but we won't talk about it in today's class. So these are the two things I'm going to talk about. And the picture I wanted you to have in the head was the following. This is my set S. This is my x star. This is my h of x equals to 0 manifold. And x star is a local minimum. And this is my x1, x2, x3. And this is how the sequence is going to converge to x star. Okay, so let's get into the proof. So first of all, I know that fk xk is less than fk x star. Can someone tell me what fk of x star is? What is fk of x star? So if I substitute x star here, what do I get?
I have one question.
Yes.
What's AMK and finally?
Lagrange multiplier theorem.
Okay.
Yeah. Okay, so what does x star satisfy? So I have f of x star plus k over 2 h of x star. What is h of x star? X star lies on hx equals to 0 manifold. So h of x star is 0. And x star minus x star square 0. So this is equal to f of x star. This means that limit k goes to infinity, norm of hx k will go to 0. And the reason for that is I have f of xk which is bounded. I have this k over 2 term which is going to infinity. I have this term which I don't know where this particular h of xk value is going to be. I have xk minus x star which is bounded. And this whole thing is bounded from above by f of x star. Okay? So if you have a term where one term is going to infinity The other term, you don't know where it's going to be, and it's all bounded from above. What does that mean? This term must go to 0, right? So that's why, as I let, so once I know that fk of xk is less than equal to f of x star, the limit of h of xk will be equal to 0. Xk is bounded, so this is the first fact. Second fact, xk is bounded. Sequence, so this implies that there is a convergent subsequence. xkl is convergent, and naturally it converges convergent to a point x bar such that h of x bar equals to 0. So this implication comes from what is known as Bolzano-Weierstrass theorem. We didn't talk about it in the beginning of the lecture when we were talking about subsequences, but the theorem says that if you have a bounded sequence in Rn, then there is a convergent subsequence within that bounded sequence. So it converges to a point f of x bar such that h of x bar equals to 0. Now the third implication from this fact is f of x bar plus alpha over 2 x bar minus x star square is less than equal to f of x star, which itself is less than equal to f of x bar. Okay, why is this the case? Well, this is the case because I'm just letting fk of xk, I'm taking the limit. Let me just write it. This is limit L goes to infinity fkl xkl. This is because x star is a local minimum. On the manifold h of x equals to 0. Okay, so bunch of things happening. Everybody understands fact 1. Everybody understands fact 2. I'm going to use fact 1 and 2. So I know that this term is less than equal to f of x star. I'm going to let the limit L go to infinity. So then I get this particular term, which is less than equal to f of x star from this statement. And then I know that x star is a local minimum. That's by assumption of the Lagrange multiplier theorem on this manifold. So f of x star must be less than equal to f of x bar. Okay, that's just by definition of local minimum on the manifold. What does this imply? What does third imply? This is 1 and 2 implies this. 1 implies this. Okay, so I have x bar which satisfies this condition. So f of x star is less than equal to f of x bar, and f of x bar plus some positive number multiplied by potentially a positive number is less than equal to f of x star. What does that imply? Yes?
Does it involve like convex?
It doesn't involve anything complicated. It's something simple. So I have a number and I'm adding a positive number to it. I get a number which is less than equal to the number itself. How can that happen? Yeah, so it's equal, it's going to be the case if x bar equals to x star. If that is the case, this term gets killed, so this is equal to 0. So I have f of x star equals to f of x star equals to f of x star. Okay, so this implies, so 3 implies x bar equals to x star. So this is the roundabout way of saying that this sequence xk is going to converge to x star. Okay, the reason to cover this proof is not because you will remember the proof for the rest of your life, but the reason is you get an understanding of how exactly to do proofs for optimization methods. And some of you may be doing research in optimization and you might have to come up with algorithms to solve problems in the future. And roughly, you will take multiple steps in order to prove that your algorithm is converging to the optimal solution. So I just want to give you a sense of how these proofs work. I don't expect you to remember this proof, and I don't expect you to remember this proof in examination, but I still want to cover it in the class, even though it's somewhat complicated.
The theorem itself is stated here, right?
No, the theorem is not stated here. The theorem was stated in the previous lecture. It's a pretty long statement. So if x star is optimal and regular, then there exists Lagrange multipliers lambda star such that something happens. Okay? So I'm just continuing the lecture from there. Okay. Everybody agrees with this? Any questions on this side? No? In which case I'm going to erase the board. Okay. Gradient k fk xk equals to 0. So remember that for k sufficiently large, so I could be on the surface of the sphere for most of the time, but after a certain point of time, remember that my sequence is converging to x star, so eventually I'm going to be in the interior of this particular ball, S. When I go into the interior of the ball, let's say this is x 10 raised to 6, x 1 million. So after x 1 million, all the points are going to be in the interior of the set, as a result of which the gradient of fk is going to be equal to 0 at xk. Because my feasible direction, remember here, I can move in any of these directions. Consequently, my gradient must be equal to 0 at the optimal solution, because xk is the argument of this function fk. So what does the expression for this gradient mean? Oh, xk minus x star. Okay, so this is equal to 0. Now from assumptions, x star is regular implies gradient hx star is full rank, which implies gradient hx star transpose gradient hx star is invertible. This is from linear algebra. So I have a full rank matrix, then the matrix transpose the matrix is invertible. So this is the assumption. Remember, in Lagrange multiplier theory, we made the assumption that x star is regular. What that implies is the derivative of h at x star is a full rank matrix. Remember, this is a matrix in Rn cross m, and this is a matrix in R m cross m. It's a symmetric matrix in R m cross m. It's an invertible matrix. Okay, so what I'm going to do is I'm going to multiply this equation. So multiply equation 1 with mk equals to gradient hxk transpose hxk inverse gradient hxk transpose. This is a matrix in R m cross n. Can someone tell me what what sort of leap of faith are we doing here? Okay, so let's see. This sequence xk is converging to x star. I know that this particular matrix is invertible. Gradient of hx star transpose gradient of hx star. This matrix is invertible. How can I assume that this matrix would be invertible? Xk is not equal to x star. Remember, xk is right here. Xk is here. How can I conclude that this is invertible?
Continuity or assumes.
Right, so continuity, right? So gradient of h is a continuous function. If this matrix is invertible and xk is close to, remember, k is sufficiently large, so xk is close to x star. This matrix is invertible. This matrix is approximately equal to this matrix. So if this is invertible, then for k sufficiently large, this is also invertible. Okay. So a lot of linear algebra stuff, whatever you have done, is getting utilized here. To see this argument, imagine if you are looking at 1,0,0,0.9. This is the matrix that is invertible. If I make it 0.9, 0.8, or maybe even 0.1, this matrix will also be invertible because it's a small perturbation to the original invertible matrix, as long as the perturbation is small. But I can make sure that the perturbation is small by picking k sufficiently large. Okay. So I'm multiplying mk on both sides of the expression. So what do I get? Mk gradient fxk plus, what do I get by multiplying mk here? Can someone tell me?
KHO.
Right, what am I getting?
KHO.
right, kh of xk. So remember this matrix, I have a matrix inverse, matrix transpose, another matrix here. So they are going to cancel each other out, and all I'm going to left with is k times hxk. I'm going to let limit k go to infinity on both sides. I get m star gradient of fx star plus limit k goes to infinity k times hxk plus 0 equals to 0. I am going to call this term lambda star. And what do I get? I get lambda star equals to m star negative fx star. This is the origin of the Lagrange multipliers. Okay, when we said that there exists Lagrange multipliers lambda star that satisfies ABCD conditions, the lambda star actually comes from here. This is the origin, this is the place where lambda star appears when you're taking the limit of k times h of xk as k goes to infinity.
What was M star? M star star.
M star is the same matrix where xk is replaced with x star. Okay, so I'm just replacing xk with x star. Okay, any questions so far? So I'm going to take the limit. So I know that k of hxk equals to lambda star. So I'm going to take the limit k goes to infinity in this original expression. So remember, I have k times hxk term here. I'm going to replace that with lambda star, and what do I get? I get gradient of fx star plus I'm taking limit k goes to infinity this was the first order necessary condition for optimality for the constrained optimization problem. Okay. So this is typically how the proof of, so this is just one way to prove Lagrange multiplier theorem. There are other proofs as well. It's just easier to understand proof, and also requires matrix, all the stuff that we have done so far, which is matrix multiplication, inverse, limits, and so on. Again, I don't expect you to remember the proof, but it's good to know what the origin of this Lagrange multiplier lambda star is. So it turns out to be limit of a sequence, and what we have proved here is that the limit exists. It's equal to lambda star, and it satisfies this particular condition, which is the first order necessary condition for optimality. Okay, you can do the same thing with the second derivative of fk, and you get the second order necessary condition, which is the d transpose second derivative of Lagrangian thing, but we won't do it in the class. But I'm happy to take questions right now. Okay. So in the previous class, we did two things. We did Lagrange multiplier theorem, and we did the sufficient conditions for optimality. Today, I want to talk about sensitivity theorem, which gives you another viewpoint of what Lagrange multiplier is. So right now, so in the previous class, Lagrange multiplier was this random vector which came out of nowhere, and it appears in the first order necessary condition for optimality. And we did an example to show how to compute Lagrange multipliers. Today we realize that Lagrange multiplier is actually limit of a specific sequence. And the next sensitivity theorem, when I talk about it, you will realize that Lagrange multiplier has a different meaning in the context of perturbations of optimization problem. So let's talk about that. So just as a side note, 5 years ago or 6 years ago, there was another graduate student in the class who looked at sensitivity theorem, and then we worked on a problem statement where he wanted a fast algorithm for driving autonomous vehicles uh, in order to optimize the energy efficiency, and we exploited sensitivity theorem to come up with a fast algorithm to do that. So since then I've become a big fan of sensitivity theorem, and I cover it in every class. Okay, sensitivity theorem. So what does this theorem say? I have a problem. I want to minimize f of x is in Rn, such that h of x equals to u. So what is this h of x equals to u term? So let's say this is my h of x equals to 0 problem. So I was trying to minimize this function over this manifold. Now u is a vector close to 0, close to origin. What does that imply in terms of this optimization problem? So I perturb this h of x equals to 0 surface a little bit. So now my surface is going to look something like this. This is my h of x equals to u surface. So I warped the surface a little bit. It's just a small perturbation to the original surface over which I was optimizing. Okay. So now, earlier I was optimizing f of x such that h of x equals to 0. Now I'm optimizing f of x such that h of x equals to u. Why would the constraint be perturbed? What are the real world situations where constraints get perturbed? So I'll give you an example, the example that we started with. I'm driving a vehicle, and I'm driving the vehicle on the highway, and a slower vehicle comes in my lane and starts driving in front of me. So earlier I was driving at 70 miles an hour. The vehicle that joined my lane came in at 55 miles an hour. Now my constraint for the velocity is perturbed. So now I have to drive at 55 miles an hour instead of 70 miles an hour. So that's a perturbation to the constraint. Okay. The weather changes every hour or every few minutes, because of which, or the radiation, let's say you are on a solar farm, there is a cloud that is going over the solar farm. So because of the cloud, there is going to be a drop in energy generation. That's a perturbation to whatever optimization problem they are trying to solve within that solar farm. So there are many situations, real world situations, because of the environmental condition, because of the way things are happening, some sort of perturbations are getting applied onto the optimization problem. And now I want to, so earlier I was solving h of x equals to 0, now I'm solving h of x equals to u. Another place where this perturbation happens. So prior to this class, there was no class in this room. So the air conditioning system of the room was trying to keep the temperature of this room constant for 0 people in the room. Now there are, I don't know, 10, 15 people in the room. Each of us are at, I'm assuming, the usual body temperature, and so we are emitting heat into this room, and now the air conditioning system is optimizing to keep the temperature of the room at a specific level, subject to so many people emitting so much of thermal energy into the room. So that's a perturbation.
Resistors that we may not know the exact resistance per volume.
So in the case of autonomous driving, you would know what the constraint is. In the case of the air conditioning system, you probably wouldn't know what the constraint is, because we don't know how many people are going to enter the class. So we won't go into that, where you have to figure out the constraints from data. But I'm teaching reinforcement learning right now. I mean, in this semester, and so there we are talking about how to use data to figure some of these things out, but not in this class.
Like, for example, in the autonomous car example, let's say X is actuator volume,
right?
For example, and there may not be, or you might have a situation where you say that, okay, apply 10 Newton, but maybe you are, because of a bunch of uncertainties, you are applying 10.0001.
Yeah. That can happen. Yeah. Okay. So let's say the optimal value is given by P of u. So P of u is f of x star of u, where x star of u is the argument of this particular problem. I'm going to make some assumption. So first is, and then let's assume that lambda star u is the Lagrange multiplier, corresponding Lagrange multiplier. So I'm going to assume that
lambda star u, what was that?
Lambda is a Lagrange multiplier. Lagrange multiplier corresponding to the constraint. Okay. So x star is the solution, lambda star is the Lagrange multiplier. So let's say x star 0, lambda star 0 satisfies sufficient condition. We covered the sufficient condition in the previous class. So this is my assumption. X star 0 is regular point. Remember that regularity was not required for sufficient condition, but here we are assuming regularity in addition to assuming that the sufficient conditions are met. Then there exists a sphere S in Rn such that x star u, lambda star u exists for all u in Rm, all u in S. This should be Rm. So there is a sphere S in Rm, an open set S in Rm such that S is open. So how do there exists open set S in Rm such that this exists for all u in S. Certainly 0 is contained in S, so this is an open set around the origin in Rm. And gradient of u pu evaluated at u equals to 0 is equal to minus lambda star of 0. So this is the sensitivity theorem. Why is it called sensitivity theorem? Okay, so let's think about it. I'm solving this perturbed problem. I'm getting an objective function. I'm getting an optimal value with respect to u. I take the derivative of the optimal value with respect to u. I recover negative of the Lagrange multipliers. Okay. So let's say I want to compute Pu. This is equal to P0 plus gradient of u Pu u equals to 0 times u. Well, I wouldn't say this is equal, but this is approximately equal. What is this equal to? P0 minus lambda star transpose u. So what that means is, if you perturb the optimization problem, the value that you are going to see is approximately equal to the value that you were seeing when h of x was equal to 0 minus lambda star transpose u. Whatever the Lagrange multiplier you found multiplied by u is the total value, optimal value that you are going to see approximately if you perturb the constraint a little bit. And that's what the meaning of sensitivity is. Sensitivity means something is getting perturbed and we are trying to understand what is this, how much sensitive this is with respect to this perturbation. And this one tells you exactly that particular relationship, which is how sensitive the optimal value is with respect to the perturbation in the constraint. And that gives you another meaning of what Lagrange multipliers mean in a specific optimization problem. A general thing which depending on whether you are solving these problems or not, typically speaking, when you're solving an optimization problem, people tend to discard the Lagrange multipliers completely. They are like, we care about x star is what I'm going to apply on the engine, on the wind farm, on the solar farm, and so on. I'm going to throw away lambda star completely. I don't subscribe to that sentiment. I think that lambda star is a very important quantity because of this result. And I feel that depending on the situation, depending on the application, it can give you very crucial information about that specific system. And it really depends from one system to another. So for instance, in the context of autonomous driving, one of the things we did was looked at the Lagrange multiplier. And if the Lagrange multiplier is large, we will run the optimization solver over and over. If lambda star is small, we won't run the optimization problem. So we use some sort of thresholding rule with respect to lambda star in order to know whether the solution is close to the optimal or not close to the optimal. So there are signals you can get from lambda star by looking at the value of lambda star. Again, it's not something that I'm just making a side comment here because I've used it in my research earlier, and I think it might be valuable to some of you who might be doing research into topics of constraint optimization. Any questions so far? Okay, wonderful. So we talked about sensitivity as well. The next topic that I want to talk about is problems with inequality constraints as well. So that's studied under the umbrella of KKT theorem. So let me just introduce the problem and then we will reconvene on Friday. And I'm going to talk about KKT theorem in that particular class. So you can think of it as a generalization of Lagrange multiplier theorem to problems with inequality constraints. So the setting is as follows. I want to minimize f of x such that h of x equals to 0, g of x is less than equal to 0. H is a function from Rn to Rm. G is a function from Rn to Rr. So I have M equality constraints, I have R inequality constraints. Generally speaking, in real world settings, M would be very small. You may have 2 or 3 equality constraints. So let's say N is 100. You may have 10 equality constraints, but you may have 1000 inequality constraints. Okay, so the number of inequality constraints typically far exceeds the number of equality constraints in typical optimization problems that you might encounter.
And if they are not defined.
Sorry? Yeah, this one is a general constraint, so they need not be affine. The affine constraints we already covered in the optimization over convex set kind of thing. So right now we are talking about optimization over general nonlinear functions and so on. So this need not be a convex set at all. Okay, so the kind of problem statements we are trying to solve is you have this h of x equals to 0 manifold, and then I'm going to make a cut within this manifold. This is my g of x less than equal to 0 set, and I'm trying to optimize the function in this particular region. So remember, h of x equals to 0 is a fairly large, it can extend all the way to infinity manifold, and I'm going to cut a small piece out of this manifold, and I'm only optimizing the function over this small piece of nonlinear manifold. Okay, that's what this problem is trying to study. Now the question is, what's the sufficient condition and necessary conditions for optimality? So that's the part. So the necessary condition is Kikiti theorem. We'll talk about it. It's a extension of Lagrange multiplier theorem to this sort of setting. And sufficient condition is again similar to Lagrange multiplier theorem, but there are some peculiarities in that particular sufficient condition. So we'll talk about it in the next class. And then we will jump into algorithm design. Okay. So far we talked about necessary and sufficient conditions for 2 settings. One is with equality constraints, one is with equality and inequality constraints. And then we'll start talking about algorithms. So next class is theory. Next Monday, we'll start getting into algorithms. Thank you.